Refraction of light. When a light ray passing from one medium to another medium, it bends. This phenomenon is called as refraction. Why the light ray is bending? When a light ray travels from one medium to another medium, the speed of light changes. So, it bends. Let us take a few examples to understand this. Here, the pencil looks like bending because the speed of light is in air and water is different. That's why it bends. This phenomenon of bending of light at the interface of two media is commonly known as the refraction of light. The bending of light ray depends on the refractive index of two media. Let us take another example to understand the refraction. Here, in this glass, you can observe an arrow mark. Carefully observe the direction of arrow mark. See, the direction of arrow mark is reversing because of refraction of light. Behavior of light ray during refraction. When a light ray traveling from one medium to another, it doesn't travel in the same direction, it bends. This is called refraction, and the bent ray is called a refracted ray. And the perpendicular line striking on that point is called as normal. Light can bend towards or away from the normal line. Let us see examples. When light travels from rarer medium to denser, it bends towards the normal line. When it travels from denser medium to rarer, it bends away from the normal. Here, the light traveling from air to water, so it bends towards the normal. When a light ray travels from glass to water, that is, denser to rarer, it bends away from the normal line.
Hi everyone, this is Irfan. So now we are going to discuss about refraction of light. What is refraction? When we observe this phenomenon, so let us try to understand about this quality of light. See, the light travels from one medium to another medium. What is the speed of light in vacuum? So the speed of light in vacuum is 3 into 10 to the power of 8 meters per second. That means around 3 lakhs kilometers per second. With this much of speed, the light travels in vacuum. When it travels from one medium to another medium, what happens? When the medium changes, the speed of light changes. That's why the light bends. That means it changes its direction. This quality of light is called as refraction. Let us try to understand this quality with some examples. So here I have a pen. Now I am going to put this pen into this glass of water. What happens? Observe carefully. You can observe the difference in the pen which is inside the water and which is outside the water. See, the part of pen which is inside the water, it is looking bigger than its original size. And also at the interface, that means where water and air meets, at the interface the pen looks like it has bent. Is the pen originally bent? See, the pen is not bent, it is straight in direction. When I put this pen into the water, it looks like it has bent. This quality of light is called as refraction. Why this is happening? Because the speed of light is changing. Here we have air and here we have water. That means two different mediums. When the light is traveling from air to water, that means two different mediums. So it looks like the light ray bends. This quality is called as refraction. Let us take one more example. Here I have a lemon. Observe the size of the lemon now. What happens when this lemon is placed inside the water? So into this glass of water, now I am going to put this lemon. Observe the size of the lemon now. So it is looking bigger than its original size. Why this is happening? This is also because of refraction. Now in this class we are going to discuss why this is happening. Why some objects are looking bigger than their original size. Why the light ray bends. So these are the topics now we are going to discuss in this class. See, just before we have discussed that when light travels from one medium to another medium, it changes its direction. That means it bends because the speed of light changes. How the speed of light changes? How to find this quality? Now let us discuss. First of all, let us take this case. That means when light ray is traveling from air to glass. So two different mediums we have. So in this case, the light ray is traveling from air and it is entering into the glass. What happens? Before going to that, let us try to know few basic concepts of this topic. So this light ray which is traveling, this light ray is called as incident ray. So the light ray which is passing into the another medium is called as incident ray. And the light ray which is travel into the another medium, this light ray is called as refracted ray. Now, if we observe carefully, the angle between the incident ray and this line n dash, this perpendicular line is called as normal line. So the angle between the incident ray and the normal line is called as angle of incidence. It is denoted by small I. And here the angle between refracted ray and the normal line is called as angle of refraction. It is denoted by small r. How these two values are, now we are going to discuss. Let us take the first case. That means when light ray is traveling from air to glass. So in this case, the light ray is traveling from air to glass. So this air is called as a rarer medium and this glass is called as a denser medium. That means when a light ray is traveling from rarer medium to denser medium, what happens? How the light ray bends. So if you observe this diagram carefully, when the light ray is traveling from rarer medium to denser medium, the angle of incidence is greater than angle of refraction. That means the refracted ray bends towards the normal line. When a light ray passing from rarer medium to denser medium, it bends towards the normal line. That's why the angle of refraction decreases than the angle of incidence. So in this case, the angle of incidence is always greater than angle of refraction. Let us take another case. That means when light ray traveling from denser medium to rarer medium. That means when a light ray is passing from glass to air. In this case, how it changes? Let us try to discuss. So this is the incident ray. This is the incident ray. That means the light ray is passing from glass to the air. That means from denser medium to the rarer medium. So this is angle of incidence and this is angle of refraction. The angle between normal line and incident ray is called as angle of incidence, and the angle between normal line and refracted ray is called as angle of refraction. So here in this case, how these two are, if you observe this diagram carefully, you can easily find out that the angle of incidence is less than angle of refraction. That means when a light ray passing from denser medium to the rarer medium, it bends away from the normal line. It bends away from the normal line. That's why the angle of refraction is always greater than the angle of incidence in this case. So angle I is less than angle R. So this is the relation between angle of incidence and angle of refraction in this case. And now, how to find the speed of light and how to compare the speeds of light, how to compare the materials. To understand this, we need to understand another concept, that is refractive index. So what is refractive index and how it is useful for us? So the refractive index, it is denoted by small n. What is refractive index? So the refractive index is this is also called as absolute refractive index. The absolute refractive index is defined as the ratio between the speed of light in vacuum to the speed of light in a medium. So speed of light in vacuum is denoted by C, speed of light in a medium is denoted by V. Then we can write the formula for the refractive index, that is absolute refractive index, N is equals to C by V. So this is the formula to find the refractive index of a medium. So speed of light in vacuum, its units are meters per second. Speed of light in a medium, its units also meters per second. So these two will get cancelled. So that's why we can get 1. That means the refractive index has no units. There are no units for refractive index. It is a constant value. Now, how this refractive index helps us to understand the nature of a material. So, as the refractive index of a material increases, the speed of light decreases. That means the material which has very less refractive index, the speed of light is very high in that material. If the material has very high refractive index, the speed of light is very less in it. For example, if you take air, the refractive index of air is 1.0003. That means almost equal to 1. That's why the speed of light in air is almost equal to the speed of light in vacuum, approximately equals to 3 to 10 to the power of 8. If you want to say exactly, the speed of light in air is 2.97 into 10 to the power of 8. That means almost equals to 3 to 10 to the power of 8. If you take diamond, the refractive index of a diamond is 2.42. So the refractive index of a diamond is 2.42. That means it is 2.42 times to the refractive index of air. That's why the speed of light in diamond is very less. The light travels very slowly in a diamond. That means the speed of light depends on the value of refractive index. So by knowing the refractive index value, we can easily find out the speed of light. That means how it travels in that medium. So these are the concepts Basically, we need to understand in the case of refraction.
Relative refractive index. When light travels from one medium to another medium, the speed of light changes. So it changes its direction. That means it bends. Let speed of light in medium 1 is v1, speed of light in medium 2 is v2. The ratio of speed of light in medium 1 and speed of light in medium 2, that is v1 by v2, is a constant. So the refractive index of medium 2 with respect to medium 1, that is n21, is equals to v1 by v2. Same like that, refractive index of medium 1 with respect to medium 2, that is n12, is equals to v2 by v1. If we take the product of n12 and n21, that is v2 by v1 into v1 by v2, it is equals to 1. By this, we can conclude that n12 is equals to 1 by n21. Snell's law. The angle of incidence and the angle of refraction satisfy the equation sin I by sin r is equals to n. Place a semicircular glass disc as its diameter coincides with interface. Point a laser light as the light propagates from air to glass through the interface at point O. Let the angle of incidence is 5 degrees. We got angle of refraction as 3 degrees. If angle I is equals to 10 degrees, we got angle R as 7 degrees. If angle I is equals to 15 degrees, we got angle R is equals to 10 degrees. If it is increased to 20 degrees, we get angle R as 14 degrees. If the angle of incidence is 25 degrees, we will get the angle of refraction as 17 degrees. We can continue the experiment like this with the different angles of incidence values. Let us tabulate the angle I and angle R values and try to find out the ratio between sin I and sin R. In this table, we have tabulated the different angle of incidence values and the correspondence angle of refraction values. So here we also calculated the sin values of all angle of incidence values and also the sin values of all angle of refraction values. In the last column, we have calculated the ratio between sin I and sin R. If you observe all these values, these all values are almost equals to 1.4. This constant value denotes the refractive index of the material of glass disc. So if we get the average of all these values, that means the average of all sin I by sin R values, we get 1.45. So this value denotes the refractive index. Hi friends, in this class we are going to discuss about total internal reflection. We know that when a light ray is passing from denser medium to the rarer medium, it bends away from the normal line. Hence, the angle of refraction is greater than angle of incidence. Gradually, if the angle of incidence increases, the angle of refraction also increases. At a particular angle of incidence, the refracted ray just grazes. If we observe the third diagram, as the angle of incidence increases, the angle of refraction grazes with the interface. That means for some angle of incidence, the angle of refraction has become 90 degrees. This angle of incidence is called as critical angle. That means at critical angle, the angle of refraction is 90 degrees. If the angle of incidence is further increased, observe the green colored line here. Here, the angle of incidence is greater than the critical angle. For this angle of incidence, the light ray doesn't undergo refraction. Here we observe reflection. That means if the angle of incidence is greater than critical angle, the light ray undergoes reflection rather than refraction. This is known as total internal reflection. There are some conditions for the total internal reflection. The first one, the light ray should travel from the denser medium to the rarer medium. The second one, the angle of incidence in denser medium should be greater than the critical angle. Let us try to understand this with an example. To observe total internal reflection clearly, we need a laser light and an aquarium. Here, if we want to observe this phenomenon clearly, better to add few drops of Dettol into the water. So observe here carefully. Here we are sending a light ray from one side of the aquarium. Here we can observe clearly that the light ray is reflecting into water itself, but it is not refracting into the air. Observe carefully. Here the water is reflecting into the same medium, that is denser medium. This is an example for total internal reflection. Now, in this class, we are going to discuss about one of the important topics, that is applications of total internal reflection. So here are the few examples for the total internal reflection that we observe in our daily life. The first one is formation of mirage and brilliance of diamond and optical fibers. Let us discuss one by one. First we discuss about the formation of mirages. So here is the image which shows the formation of a mirage. Mirage is an optical phenomenon that creates illusion of water. These are most commonly observed on sunny days when driving down a roadway. On sunny days, surrounding air is heated to high temperatures. Hot air tends to be less dense than cooler air. When light travels through a non-uniform medium, that means hot air, cool air, that means different medium, it follow a curved path to reach observer's eye. So you can observe this in the diagram. So a curved path of light ray traveling to the observer's eye. Now observer receives two rays from the object. One is direct and other is curved. You can observe these two rays in the diagram. One light ray which is showing directly, that means straight line, and another one is curved line. So that's why the illusion of water takes place. So next we discuss about the brilliance of diamond. See, here you can observe how the total internal reflection takes place in a diamond. The refractive index of a diamond is 2.42. When light travels from A to diamond, its speed decreases 2.42 times. The critical angle of diamond is very less, that is 24.4 degrees only. So by polishing the diamond with specific cuts, it is adjusted that the angle of incidence is more than the critical angle. We know that when the angle of incidence is more than the critical angle, there the total internal reflection takes place. So hence, it suffers multiple reflections and gives the diamond a sparkling brilliance. That's why a diamond shines when a light ray is dispersed on it. And now we discuss about the another example for total internal reflection, that is optical fiber. One of the most important application of total internal reflection is optical fiber. So an optical fiber is given in the picture. Observe it carefully. So how the optical fiber works? Let us learn. When light enters the core of glass fiber from one end in such a way that the angle of incidence is greater than critical angle, it suffers total internal reflection and emerges from other end. You can observe this in the picture. See, the optical fiber contains few parts, that is core. See, you can observe the light ray is entering from one end of the fiber optics. So when it enters into it, that means the angle of incidence should be greater than the critical angle of that glass material. That's why it takes reflection and travels. You can observe this phenomenon in this diagram clearly. So where we use these optical fibers in our daily life? So these optical fibers are used in optical communications, and also we use this in endoscopy. So endoscopy is one of the tests we take in the medical field.
Hi everyone. Now, in this class, we are going to discuss about another new concept of refraction of light. Now, here you can observe a glass slab. In my hand, I have a glass slab. I don't know the refractive index of this material. Then how to find it? There is a procedure to find the refractive index of an unknown material. Let us try to do this experiment and find the refractive index of this glass slab. So here we have a glass slab. Now through this glass slab I am going to send a laser light ray. Now I am sending the laser light ray perpendicular to the glass slab. Observe carefully how the light ray will travel through the glass slab. Now you can observe the light ray passing through the laser light. you can observe the image of the laser light on the screen. What happens when I remove the glass slab? Observe carefully. When I remove the glass slab, there is no change in the position of the image. See, observe carefully. So the image is not changing when the glass slab is present or when it is removed.
When we send the laser light ray making some angle with the glass slab, the position of the image changes. Observe carefully on the screen.
Now I have took this glass slab and now I am going to draw the outline of this glass slab. So here I have drawn the outline of this glass slab and now I am going to name these vertices as A, B, C and D. Now what we have to do, we have to draw a perpendicular line to this AB surface. I will draw one perpendicular line to this AB surface. First let me extend this AB surface and now I will draw one perpendicular line to this AB surface. Now what to do? To this perpendicular line, I have to draw one parallel line. That means one parallel line to AB anyway on this perpendicular line. See now, let us name this as PQ. See, PQ is parallel to AB now. Now what I have to do? I will take one pin and I will put this pin on PQ. And now I will put the glass slab in its original position. Now observe this pin through the glass slab. I have took another pin here. Now what we have to do? We have to adjust this pin as it coincides with the another pin. That means these two pins have to make a straight line. See, carefully observe. Now these two pins are looking like they are in a straight line through the glass slab. Are these two actually in straight line? Let us try to observe. See, these two pins are not in a straight line. So there is a gap between these two pins. Let us try to locate the point of the second pin. Let us suppose now the pin has been located. This difference, that means this distance between the two pins is called as vertical shift. Let us try to calculate the vertical shift. First of all, I will remove the two pins. Now let us try to calculate the vertical shift and then the refractive index of this glass slab. Let us measure how much the vertical shift is. This distance. This is 0.8 centimeters. So the vertical shift of this glass slab is 0.8 centimeters. Now let us measure the thickness of the slab. It is 2.1 centimeters. So the thickness of the glass slab is 2.1 centimeters. How to find this? Here is a formula to find the thickness of the glass slab. So here is the formula to find the refractive index of the material. So refractive index N is equals to thickness of the slab by thickness of the slab minus vertical shift. So just before we have calculated, that means we have measured the thickness of the slab, that is 2.1 centimeters. And now we have experimentally calculated the vertical shift of this glass slab. How much it is? It is 0.8 centimeters. By substituting all these values in this formula, we get n is equals to 2.1 by 2.1 minus 0.8. By calculating, we get the value, the refractive index n is equals to 1.615. So this is the refractive index of the given glass slab. So the refractive index of this glass slab is 1.615. So there are no units for this because it is a constant value. It is the ratio between, refractive index is the ratio between two same quantities. That's why it has no units. It is also discussed in the previous class. So like this, we have to find out the refractive index of an unknown object by finding its vertical shift.